In the previous videos, we saw the battery pack protection management features of the battery management system, or BMS. We saw how BMS will protect against an overcharge and over discharge situation. We saw how it will protect against an undervolt or overvolt situation. Similarly, we saw how we can detect the thermal anomaly of the system and thus employ a proper thermal management system for the battery pack protection. Now in this video we are going to look for the capacity management. So we worked around the electrical management protection part, so the peak discharge, peak charge points, and then depending on that we set upper and lower thresholds for the charge and discharge, and BMS will continuously monitor these things and act accordingly. Similarly, for the voltage also, it will set up the upper and lower thresholds. We have to feed in this data to the BMS, and then it will automatically keep monitoring the whole battery pack and protect against any overvolt or undervolt situation. Okay, so now for the capacity management, it is very much important to have the battery pack cells at the same level of charging. So or charge, or say the voltage, right? So in a balance pack, in the first section of this slide, you see that each cell is having the same sort of voltage. So each cell is having a 3.2 volt. So there is no difference between them. When we charge this pack, we will charge all of the cells at an equal rate, and we will cut off. So we don't know about each cells, but we will cut off the whole setup when we reach individual threshold for that particular cell. So if a cell is having a upper threshold of 4.2, we will cut off the whole charging process at 4.2, right, in order to protect against the overcharge. So now what will happen if we have an unbalanced battery pack like this? So this cell will reach its potential 4.2, this won't, so it will be 0.2. So this capacity of the battery will drop significantly, right? So in case of a cell 3, there is a very large difference of about 0.7 volts, right? This looks very small at an individual cell level, but when you are looking at a very big battery pack of an EV, so where we are looking at more than 1000 cells, so this 0.7 volt will make about 70 volts of difference, and which is very significant when we compare the operating range of the electric of the battery, right? So it's not like 1 to 4.2, it's 2.7 or 2.6 to 4.2. So already we are working at a very small range, and out of that, if you take out such a large portion, then the capacity will reduce drastically. So there comes in the picture of cell balancing, right? So what BMS will do, BMS will use a discharge resistor, and excess voltage of the cell 1 will get converted into heat and then dissipated via the thermal management system, right? So we are going to model the same control system in the MATLAB, and we will see how this whole thing works. So I'll just quickly launch MATLAB and then Simulink. We will create a blank model. Okay. So to begin with, we will first add battery, and now we are using a battery from electrical subsystems, so as the specialized power systems. So I am using this particular battery. You can any battery type. You have to be careful with the port selection. So the connections which we are going to make in this case are going to be electrical in nature. So the MATLAB power systems. Now if you want to use a physical system, which is fine, you can use other battery types also, but there will be some workaround for that. So let's set the initial parameters directly. So we will use a preset thing. So we want to simulate temperature effects. We want to use a preset battery of 3.6 volt, 4.5 ampere hours. We want to simulate aging effects as well, and the initial state of charge of this battery I want to be 80, and the battery response time is very very low, and which is 1 seconds, right? So we will save this thing. we'll just quickly check if everything works. And then discharge, temperature, EG. Yeah. We'll quickly close this, and then you see we have one more port appearing. This is the ambient temperature port for us. Right. Like we are going to use 3 such cells, and these all will be connected in series. So it's negative, it's connected to positive, and then it's negative, it's connected to its positive. Okay, and then we are going to add a ambient temperature. So we are going to use a constant which will be say 25 degrees Celsius in our case, and then we will just add this constant to the whole system. Let's just rotate this thing and make it in line with all. You can obviously use 3 different ambient temperatures, and which is perfectly fine. You can do that too if you want to introduce a deliberate thermal anomaly to the system. For now we will use a single ambient temperature for the simplicity. After this we are going to add an ideal switch. So an ideal switch, and we will change its parameters. We don't want the measurement port, so we'll just disable that, and yeah, everything else is okay. And then we want to connect this thing to the positive side, and we want to repeat this for all. It is not connecting. Okay, now it's done. And then yeah, so we have added switches. So we have to add one more series RLC load. So we'll just type series RLC load for this, and we obviously have to make some changes because we don't need that capacitance part, so inductance and capacitance part, so we will just we remove those things. Okay, so for the nominal voltage of the battery pack was 3.6, so we'll look for around 4, and then frequency 0.1, and the active power is 1000 at this situation. Inductance is nothing, so there is 0 inductance involved, make it 0. And the reactive power or reactive power is again 0, so we don't have any inductance and capacitance to the system. It's 4, 0.1, 1000. Okay, now it becomes like a normal RLC load. We'll rotate this thing, make it a little bit smaller if possible. Yeah, and then we have to connect this into the same fashion as we saw in the PPT. Negative will get connect here, it goes here, and then the gate it goes here. We can make it a little bit smaller so we can fit. Okay, yeah, so this is the RLC load, and we have to repeat the same procedure for all 3 again. And just quickly copy paste, and I'll repeat the procedure. now we have connected this thing. So now I want in a voltage measurement. So voltage, now voltage sensor will not work here, but we can use a voltage measurement because of the simulating power systems requirement. So we will just connect to a negative and this to a positive part, which is here, and then we can obviously add a scope to monitor this thing, and then a display to show us what is happening. Resize the window. Okay, we can just draw, make it a little bit closer, and then yeah, now we need to add these gates. So how the gate switches work is from the logic, either 0 or 1. 0 means off, 1 means on. Okay, so or you can say 0 means disengaged, 1 means engaged. So now we have to pass this thing into a product block. So I'll just use a product block here. Let's just rotate it, and then we will use the output port of the product to the gate. Now I want to do the same thing for all three again. Okay, and then we are going to use a from block, right? Yeah. It will just work properly. The next thing we will just connect to each. So what I want to do is I want to connect this to a constant block which will have a value 1. So I'm using this constant value to act as a trigger. And then similarly I want to change the from block name, so that tag for this will be S1. Similarly, we'll just copy paste these things. Right, we will change S4. One is S1. S means switches. So S for switch 1, S for switch 2, S1 switch 1, switch 2, switch 3, S1, S2, S3. And now we have this constant block over there. We have display, we have this thing here as well. And we got the ambient temperature. Now we have to feed in some SOC, state of charge data. So now this port, when connected to a bus selector, I'll just quickly go and add a bus not bus creator, a bus selector. We'll just go for, we'll take this bus selector here over here, and then you want to connect this to this. You can select the bus selector, and then we can select what signals do we want. Okay, so this is what the first bus, this connection from the battery. This port can show the age, the maximum capacity, ambient temperature, cell voltages, and etc. So what we are interested in is state of charge, which I want. So these and these I want to remove. State of charge is the first one which I want. Then I want current, select, and then I want voltage, select, and then I want cell temperatures, select. So we can change the order, up, then this can go down, and okay. So now we have four outputs of this thing, right? Let's just move. Okay. So now again we are going to do the same thing for the S3. You have to remember the order which we have selected here: SOC, current, voltage, and cell temperature. You can see, obviously you can see here as well, but so now let's get some vector concatenate, change the direction, change the number of input to 3, because we are going to have 3 set of data from each batteries. So for this will get connect. This is SOC of 1, this is SOC of 2, this is SOC of 3. Okay, and then either you can connect to a display, or you can connect to a scope, or you can do both. Let's increase the size of this display, because we are going to see 3 to 4 entries here. So now we have to repeat the same procedure again and again. So for now I'll just remove this, because I can use this block, copy paste, arrange it, copy paste, arrange it, copy paste. So 4 sets of this thing, and then let's connect. So first is SOC, so this is showing SOC to us. We'll connect each SOC. Then second is current, so we are going to add current port from all. Then we want to look at the voltage, so voltage from each and every one, and then the last, cell temperatures. You can make mistakes here because these connections are a little bit confusing, but you just have to follow the same order. So first port, first cell, second port, second cell, third port, third cell, and similarly this one is SOC, this is current, this is voltage, and this is cell temperature, exactly as we have selected in the bus selector part. And now we have to have some go-to blocks available with us. So let's get some go-to block, rotate them. We are going to feed on the SOC, so SOC1, and copy paste. So this will be SOC3, 3 SOCs for 3 different batteries, SOC2. Now we will just connect them. So SOC1 here, SOC2 here, SOC3 here. So now we have all 3 SOCs with us. So our model is almost done. We just have to include a MATLAB function, because see what will happen during the passive cell balancing. There will be some logic, so we are going to inbuild that logic right now in this model. So but let me tell you what will happen hypothetically. So say this battery is at state of charge of 65%, this battery is at state of charge of 80, and this battery is at state of charge of 100. So this is for obviously they will have different voltages with respect to their batteries, with respect to their state of charge, but now I want to balance these cells, right? So what I will do, I will first find out what is the lowest state of charge available in the whole system right now, and I will dissipate the additional voltage available on the other cells using this discharge resistor. So I'll just add a MATLAB function there. This is a user defined MATLAB function, and we will just write some code. Okay, So we are going to create a function s1, s1, s2 and s3, so which is for our switches. And then for the function you can go with the u1, u2, u3, depends on you, because we are going to use these go to and from blocks and pass values into this functions. Okay, so this was it. We don't want to close right now. And then I'll just write the code. u1 equal to integer 32. I'm defining each term right now. And now we are going to add a if else loop. So if my u1 is greater than my u2, which is SOC1 and SOC2, and so if u1 and u2, u1 is greater than u2, or u1 is greater than u3, basically I'm using an OR logic here. I can add some spaces too. Okay. S1 or switch 1, make it 1, else S1 is 0, means it's off. Similarly, if u2 is greater than u1, or u2 is greater than u3, s2 equals 1, else s2 equals 0. Similarly, if u3 is greater than u1, or u3 is greater than u2, s3 equals 1, else s3 equals 0. And we'll just quickly save this MATLAB function. Okay, we can save this to the MATLAB, or we can call it passive surveillancing, etc. So I've added a MATLAB function here, right? And then I'm going to use these from our go-to blocks as well. So let's get to the from block. So from SOC1 connect to U1, copy paste, SOC2, SOC3. This is done. Now I'm going to use go to block for the S1 switches. S1, S2, similarly S3. We'll just save the model and we will check the connections once again if you have missed something. So yeah, now okay, everything looks fine. Let's run the system. Okay, we have some errors. Failed to evaluate mask initialization. Okay, one thing I left out was the continuous or power GUI block. The power GUI will work. Okay, you can see here it is trying to dissipate the voltage. Great, stop. We can change the stop time to infinite, so we can see the whole process happening. Okay, I'll just run this thing again. Now you have to just focus, initially just focus on this block, and we are going to repeat the simulation again and again to see any differences, or I can just open the scope for you and then we can run the system. See, these two are starting at a different. And now the red one and the blue one, they are just dropping their SOC. They are trying to maintain the SOC of the lowest cell, which is about at 60 approx. Right? And this will continue until they match. Here the simulation stop because we can just pause the simulation here and stop it. So let's just open the scope and see what happened just now. You can see here the lowest one was here. Obviously it will dissipate some energy, some SOC, because after the beginning the system will take some charge to like evaluate the process, and once it determines that okay, this cell is having the lowest SOC available right now, meaning the lowest voltage available, then it will just it will just drop the voltage or the state of charge of other cells so that they can match, and once this cell balancing is complete they can charge again. So similarly you will see the same trend everywhere, and if you keep an eye on this thing, it just started at a different level and then they all are equal, they are roughly equal. And then you see here also cell temperatures are more or less equal, the cell voltage is almost equal, 3.688, 3.696, 3.696, etc. Now let's see what happened at the beginning. Just zoom in here and see the differences. So this is the withdraw voltage from the battery. So see the first thing, which was at about 3.6 initially, there is no discharge from that thing, and then the other two, the red and the blue one, they are discharging until about 90 seconds maybe, and then it is constant throughout. So let's run the simulation once again, and maybe we can change the parameters this time. So instead of 65, let's consider 85 for this one, let's consider 75 for this one, and let's consider 95 for this one. You keep an eye on these these displays. See now, it has detected that the cell 2 has the lowest state of charge available right now with the lowest available state of charge. So now it will just try to dissipate the excess state of charge of cell 1 and cell 3, and once that completes, simulation will stop. So now, right now they have already dissipated the heat, dissipated the state of charge via heat from this discharge resistor, and now the state of charge and the voltages are roughly matched. So this is how the whole passive cell balancing thing happens. Now why this is called passive cell balancing is because each cell is not interacting with each other. So say one cell is having a lower state of charge compared to the other one, they are not interactive at that moment. So what is happening, we have an external discharge resistor, we are flowing the flowing the current through that discharge resistor, and we are dissipating the heat while we are trying to maintain the overall state of charge and make it equal. So cell 1, cell 2 and cell 3, they all have the same voltages, same voltage and same state of charge. That's how the whole passive cell balancing thing works. I'll just save this model. And for the active cell balancing, each cell will interact with each other, so there will be some additional components which will notify each cell. So in case one cell is having 100% state of charge and one cell is having 50% state of charge, that 100% state of charge from the higher capacity cell will get into the lower state of charge cell, so and then they will get balanced at about 72-73% of state of charge each. So that's how one cell will charge the other cell. That happens in the active cell balancing. And what I have shown here, using the discharge resistor, what we are doing is we are doing the passive cell balancing thing. So when to use the passive cell balancing and when to use active cell balancing, it completely depends upon the use case and the complexity of the whole system, right? So the best use case for the passive cell balancing is when you are charging at a slow charger. So there is enough time to dissipate the heat, and then you can afford to lose the individual cell capacities. If you are using the heat, if you are using heat to dissipate the energy, then the capacity of the battery pack is reducing, right? So what it effectively means is your range is dropping if you are using the cell balancing thing. Fortunately, cell balancing is not used every charge and discharge cycle. It can, depending upon the chemistry of the cells, this thing will vary, the time span will vary, but it will usually happen at the charging station. So you are plugged in for more than 3 and 4 hours, and then that there is some differences between your cell modules. So the battery management cell will decide to either go for active or either go for passive cell balancing techniques, and then balance these cells so that any permanent damage of the battery can be prevented. Thank you.